make a big difference here if in the presidential election, if they were talking 68% confidence, they could have a pretty small error, but they're only 68% confident. There's a good chance that it'd fall way outside of that when they get to 95% confidence, which is also the media standard. Hopefully, all those percents that they're giving you in the presidential polls are to 95% confidence. And that's what the nuclear industry is 95% confidence on our measurements. And let's see how practically this percent confidence can really change how you perceive things. So let's say that we have some organization, some environmental group that's really concerned about this technical school up in Mexico, Missouri, contaminating the river. So we got this technical school, and there's this creek behind the technical school. So here's the tech school here. And turns out that this technical school also has a nuclear technology program. And so here's the flow of the creek down here. This environmental group comes down, and they grab some water downstream of this technical school. They grab some water upstream of this technical school, and they want to see if this nuclear program's dumping anything down their drains or anything into this creek that's contaminating the creek with radioactivity. Now, the idea here is if there's more radioactivity downstream of this creek than immediate upstream of the creek, there's a good chance that this school is putting radioactivity into this creek, right? So they do their measurements, and they find out that they take their water samples, and the upstream sample they measured it for 5 minutes, took a radiation detector measurement for 5 minutes, and they found out that it gave them 35 counts per minute on the meter. So counts per minute, a radiation detector going tick, 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 tick. So they got 35 radiation counts per minute on a 5-minute count. Oh, excuse me. That would actually have been, sorry about that, that's downstream. Every once in a while you got to go change things, right? So just change your notes. Downstream. Upstream, they take a 5-minute count on their sample they got from upstream, and they've got 30 counts per minute. Uh-oh. This is not looking good for the school there, folks, because look at that. It's obvious, is it not, that the downstream count is 35 counts per minute, and the upstream count is 30 counts per minute, so there's more counts per minute downstream than there upstream. It's time to bust these guys. But it's not that simple, folks. You have to remember that with every measurement, there's an error. And what we've done here is we've taken one measurement, we take another measurement, and we have to subtract the two. And whenever we took the 35 counts per minute, subtracted off the 30 counts per minute to think we got a net counts per minute, net 5 counts per minute, proving that the radioactivity downstream is higher than the natural radioactivity of the water, we got to remember that this 35 was plus or minus some error. Even our background count was plus or minus some error. Okay? Every measurement has error. And then when you subtract two things, when you do any kind of multiplication between two measurements and they have error, the errors always add. You never have errors subtracted away because you've got a measurement that's not so good. You do mathematically something to it, measurement that's not so good, and the errors just keep on combining into higher and higher errors. And we have this formula. We could do this many different ways, but we have a pretty simple formula that says that the standard deviation of any net count rate, and net count rate, net means when you take the gross, so this upstream was our gross count, and downstream, was the gross count. Upstream, we're going to call our background count because we weren't expecting to see any radioactivity up there except for what was naturally in the creek already. So our standard deviation of our net counts per minute is going to be equal to the square root of the rate of our sample count, our gross sample count. I'll just go ahead and write that as gross. The rate of the gross, or the rate of the downstream, divide by the time that we counted the gross sample count, plus the rate of our background, which is our upstream, divided by the time that we count the background. Now let's analyze this equation before we go on and just take a look at it. We want the least amount of error as possible. So on this side of the equation, we'd like to make that as low as possible. We'd like to make standard deviation low. That would mean we're more accurate, right? We have less error. Well, what can we do to make this low? Well, we can't do much about the gross sample count. And in this situation, we can't do much about the rate of the sample count. The only thing we could do is, if we counted for longer, either counted the sample or the background sample for longer, we would get narrower, less and less counts. It's kind of like when they go out to a presidential election across America, many times they count and they'll call 1,000 counters, okay? 1,000 callers, excuse me. Now I'm getting radiation and people messed up. But they'll call 1,000 people and survey 1,000 people. Now, would they be more accurate if they counted and called 2,000 people? Yeah. What if they called 2 million people and asked them who they're going to vote for? Well, then they'd be more accurate. What if there's 50 million possible voters in America, or 100 million, let's call it 100 million possible voters in America, and they call all 100 million? Well, then they're really pretty much on target, right? So the more data that you get, the more accurate you are. And that's all that's happening here, is if you count with a radiation counter this same sample longer and longer, you're going to have less and less error. But we did pretty short 5-minute counts here. Well, let's see what happens in this equation when we find out the net, we calculate the sigma net count rate. So our standard deviation is going to be the square root. Our rate of our gross, that's counts per minute, our rate of our gross was 35 counts per minute. And our time of gross, since we didn't counts per minute, better be in time of minutes. And so our time of our gross sample, we counted it for 5 minutes. And then our errors at